everyone, today our learning goal is to identify x and y intercepts of a function. We are also going to continue graphing lines and talking about transformations of linear functions. So starting off with x-intercepts, how do I find an x-intercept of any function? What you're going to want to do is you're going to want to plug in 0 or input 0 for y and solve for x. So it looks like this is an ordered pair. I'm going to be plugging in 0 for y, and then I get some number for x. So you're going to have some number replacing x. Okay, to get a y-intercept, where do you think we plug in 0? We're going to plug in 0 for x this time, and then we're going to solve for y. So what this looks like as an ordered pair is I'm plugging in 0 for x, and I'll simplify and then get something for my y output. Okay, so just practice. Number 1 says find the x and y intercept for the following function. Show work algebraically. So anytime you see f of x, you are welcome to write y if you are more comfortable with the format y equals. Okay, those are interchangeable for our purposes here. Okay, the first thing I'm going to do is I'm going to find the x-intercept. Right, so in that case, I'm going to be plugging in 0 for y. So I'm going to replace y with 0. So I'll have 0 equals 10x minus 1. Then I want to get x by itself. So I'll add 1 to both sides. To finish getting x by itself, I'll divide by 10. And I get that 1/10 is equal to x. I do not want you to leave your answer like this, though. I want it written as an ordered pair. So what did I get for x? X, I got 1/10. And x was 1/10 when y was equal to what? We plugged in 0 for y. So that's our x-intercept. For our y-intercept, where do I plug in 0? To find the y-intercept, we plug in 0 for x. So this time, I'm going to be replacing x with 0. So I'll have y equals 10. Instead of x, I'm going to plug in 0 minus 1. Notice anytime I plug in, it's just good practice to put parentheses around whatever you're replacing. Really, I could have even put parentheses around 0 over here when we found the x-intercept. It just wasn't necessary, but in this case, the parentheses are necessary so that you know that there's multiplication there. 10 times 0 would be 0. So I get y is negative 1. 0, negative 1 is how I want you to write your ordered pair for the y-intercept. I've already talked a lot about linear functions. We've been talking about using slope-intercept form, where m is the slope and b is the y-intercept. Here again it says slopes represented by m. Using slope-intercept form, it says the y-intercept's where the line crosses the y-axis. We've talked about that. The y-intercept always has an x-coordinate of 0, which is why we write it as 0, comma, some number. Okay. What we're going to be doing today is actually transforming the linear function. What is a transformation? A transformation is just any kind of change of the linear function. So if there's a change in the way the linear function looks, a transformation has occurred. Okay, we're going to focus specifically on vertical transformations today. So there's some different linear functions we can talk about, but the most basic linear function is the parent function. A parent function is just the most basic type of linear function. And in this case, the parent function looks something like this. Okay, again, this is called the parent function. It's the most basic linear function, and the parent function is y equals x. Okay, y equals x is the most basic parent function because we start at the origin and it's got a slope of 1. Up 1 over 1, so that's the point 1, 1. Up 1 over 1, that's the point 2, 2, etc. Okay. If we notice that there's been a vertical reflection, you're going to see a negative sign in front of x. So like something like this, y equals x would indicate, y equals negative x would indicate a reflection. So in that case, the line would be decreasing from left to right. If there's an a in front of x, like y equals 2x or y equals 1/2 x, that could indicate either a vertical stretch or a vertical shrink. And it's pretty obvious which one is which. Like here, if the number is bigger than 1, like 2 is bigger than 1, then what's going to happen to the slope? The slope's going to steepen, right? It's going to become steeper when a is bigger than 1. Now, if a is between 0 and 1, what's going to happen to your graph? It's going to flatten out, right? The slope is going to make it less steep. It's going to flatten out. So while this might be a pretty steep function, the 1/2 will look much flatter. Then the last thing that can happen is dependent on this plus or minus b on the back. If you see plus b, like if you see something like y equals x plus 3, that plus 3 is going to indicate up. And if you see something like y equals x minus 3, what do you think is going to happen to the graph? Well, it's going to move down. So translation and transformation sound very similar, but translation is a type of transformation. It's a type of transformation where you're sliding the graph. Okay. A reflection, another word that you can use for that would be flip, if you're not comfortable. Okay. So translation plus b means up b units. Translation down b units would be the opposite way. Let's go ahead and just take a look here at the parent function. We're going to be using the parent function quite a bit in the next couple examples. So I want to show you what the parent function y equals x looks like. So here it is. This is the parent function y equals x. You can see it has a slope of 1, and it runs through the points 1, 1, 2, 2, 3, 3. Okay, that's the most basic linear function. What I can do now is look at each of these transformations. Like, what does a vertical reflection look like? What does a flip over the x-axis look like? Well, I'm going to go ahead and just type in a negative sign in front of there so I can show you what that's going to look like. Let's see. Put a negative. See what happened to the graph? Right? It just totally flipped. Okay? So that's what happens when you put a negative in front of the graph, is it's going to cause the graph to flip. Now let's talk about if I slide this. Like, let's say this time I want a number bigger than 1. What happens when my number gets bigger than 1? What's happening to the slope? Like if my value is 3. See how the slope is much steeper? So if you have a number that is bigger than 1, it's going to vertically stretch your graph. Let me go back to 1. Let's say I have a number less than 1 in front of x. So like if I have 0.5, what happened to my slope? It got less steep, right? It got flatter. Or if I have a slope of 0.1, look how flat that graph is. Okay, that because the number in front of x is greater than 0 but still less than 1, it's going to be a vertical shrink. So anytime you see it flatten, it's a vertical shrink. Or anytime you see the graph get steeper, that would be a vertical stretch. Okay. All right, in this section we're going to graph the function f of x equals x in red. So let me grab red from my palette. I'm going to graph the parent, this is known as the parent function in red, and then we're going to find the slope, x-intercept, y-intercept of the given equation, and we're going to graph that in blue. So let's start by graphing the parent function. Again, your parent function is y equals x. You'll notice that the parent function has a slope of 1 and a y-intercept of 0. Okay, so let's graph the origin. I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. You can also go down 1, left 1, down 1, left 1, etc. Okay, that's going to give us our most basic linear function. Okay. What we want to do now is we want to compare g of x to that function. just looking at that right now, because I see that -3 tacked on to the end, I'm already thinking, ooh, down 3. Okay, but let's go ahead and graph it first before we label the transformation that's happening. Here the slope is 1, right? This is an mx plus b form, so I just grabbed 1 as my slope, and my y-intercept, that's your b value, so I can already see that that is 0, -3. Okay, so I can graph 0, -3 and use a slope of 1. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, etc. to graph that line and make it a little bit nicer. Okay, so that is my line, x minus 3. How do I find the x-intercept? Well, I'm going to plug in 0 for y and solve for x. So if I add 3 to both sides, I get that x is 3. So 3, 0 should be my x-intercept. And there it is right there. Okay, that's where it crosses the x-axis, so that looks good. If you ever want to check your work, you can just pick any x value you want to plug into the function. So if the function is g of x equals x minus 3, let's just choose some x values to plug in. Like, give me a negative x value, 0, and a positive x value. Maybe let's do -4, 0, and then give me a positive number. Maybe like 5. Okay. And again, you don't have to do this. You really just need 2 points to graph a line, but this will help us check our work. So if I do g of -4, that would look like, what would that be if I plugged in -4? -4 minus 3, so I would get -7. So when I input -4, my output was -7. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. I do have that point on my graph. Okay, so that checks out. It looks good. If I plug in 0, what does g of 0 look like? 0 minus 3. My output would be -3. Oh, I already have that point graph right there. 0, -3 is on my graph. That looks good. So far so good. And if I do g of 5, what is 5 minus 3? 2. So I should have the point 5, 2 on my graph. 1, 2, 3, 4, 5, up 2. There it is right there. Okay, so that checks out. It looks like we graphed that function correctly. This right now might feel like busy work to you, but I promise there's a reason why you're doing this. We're going to be using this notation, g of some number or f of some number, quite a bit. And I want you to understand that when you plug in an x value and you simplify, it gives you the y value that corresponds. So that's how you are always going to get ordered pair. Whatever number you plug in for x, you're going to get an output, and that's your y, right? And then you can write an ordered pair x comma y. So we're just getting practice now for later. All right, so let's compare transformations. How am I getting from the red graph to the blue graph? Use some kind of vocabulary from this word bank. Is it a reflection? Is it a vertical stretch or shrink? Or is it just a vertical slide up or down? Did I reflect my red line at all to get my blue line? Does it look like a flip? No. Did I stretch or shrink my red line? Did it get steeper or less steep? No, the slope didn't change. So really, it's got to be a translation. How do I get from this point to this point? It's going to be a translation down 3, which I predicted at the beginning as soon as I saw that -3 there. Okay, so for transformation, I'm going to say that this is a vertical translation down 3. Okay. Over here, we're going to go ahead and start by graphing our parent function again. Graph 0, 0. Up 1 over 1, up 1 over 1, up 1 over 1, etc. You're just graphing the parent function every time to have a point of comparison. Okay, so that's y equals x. And now I'm going to graph d of x. My slope is 1/3. My y-intercept is 0, -4. I can tell that from the 1/3 and the -4 up here. To get my x-intercept, I plug in 0 for y, and I'm going to use that to solve for x. So here, if I start by adding 4 on both sides, I get 4 equals 1/3 x. And then I could divide both sides by 1/3, but what's easier than that? What's the same thing as dividing by 1/3? Multiplying both sides by 3. Multiply by the reciprocal. Hopefully you've heard that before. 12 equals x. Okay, so I'm going to have an x-intercept at 12, 0. Okay, I'm going to plot my y-intercept, 0, -4. 1, 2, 3, 4. And then I'm going to use my slope of 1/3. So I'm going to rise 1, run 3, rise 1, run 3, rise 1, run 3, etc. And you can see that if I rise 1, run 3, I would end up at 12, 0. So that looks good. All right, if you want to check your work, let's just pick some x values to plug in. Maybe we do -7, 0, and 4. Okay, and we're plugging it into what function? We're plugging it into g of x equals 1/3 x minus 4. Now, if I plug in 7, or -7, what is 1/3 times -7? -7/3. Yikes. I do not want to have to do that. I don't want to have to deal with fractions. What's something that I could plug into 1/3 x minus 4 that would give us a nice number? We want something maybe that's divisible by 3, since we're going to be multiplying by 1/3. Maybe we'll do, well, let's just do -3 and 3. Those sound easy. Those would be divisible by 3. G of -3 would be 1/3 times -3 minus 4. Okay, so if I multiply the numerator by -3, I would get -3/3 minus 4, which is -1 minus 4, which is -5. Do I have a point at -3, -5? 1, 2, 3. 1, 2, 3, 4, 5. There it is. Sure do. If I plug in 0, what's g of 0 going to give us? What's 1/3 times 0 minus 4? That would be 0 minus 4, or -4. And we do have a point at 0, -4. That looks good. Okay. And then finally, if I plug in 3, what's g of 3? Oops. Let me give myself a little bit more space. G of 3 would be 1/3 times 3 minus 4. That would be, now be careful here. That's going to give me 3/3. What is 3/3? Anything divided by itself, that's going to be 1 minus 4. Notice it's 1, not 0. And then we get -3. Okay, do I have a point at 3, -3? Sure do. All right, that looks good. We graphed it correctly. Now describe the transformations to me using the word bank. Remember, we have vertical reflection, vertical stretch or shrink, and vertical translation. Did a vertical reflection happen? No, there's no flip. Did a vertical stretch or shrink happen? Did the slope change? Yeah, it flattened out. So what would that be, a vertical stretch or a vertical shrink if it flattens? That's going to be a vertical shrink if it gets less steep. Okay. And actually, I could have told you it was a vertical shrink, because look at this number 1/3 right here. See how that's a number less than 1 but greater than 0? Instantly, as soon as I saw that 1/3, I already knew that it was going to be a vertical shrink. So I'll even put by 1/3. Okay, and then what else has happened? For example, what's the -4 do? That's going to be down 4. Doesn't it look like we took this point and moved the whole graph down 4? Okay, so I'm going to say vertical translation down 4. Okay, let's just focus on the transformations of these other two graphs. I'm not going to do the XY charts for these. Okay, we already know what the parent function looks like, right? Really it goes from corner to corner if you want to graph it quick, and you know it's got to go through the origin. Okay. For the new function, it has a slope of -2, it has a y-intercept of 0, 0. I know that because there's no b value. I already talked about how to find the x-intercept. We're going to skip that here. So I'm just going to graph the y-intercept, and I'm going to use the slope. Down 2 over 1, down 2 over 1, down 2 over 1. I didn't quite get through that point. Okay. Now there's actually a couple separate transformations here. Just looking at g of x, I see a negative and I see a 2. What do you think the negative sign is going to indicate? If there's a negative sign, what's going to happen? There's going to be a vertical reflection. Okay, so I already know, just looking at that equation, that there's going to be a vertical reflection. And then what's the 2 going to do to the graph? 2 is a number greater than 1, so I should expect the slope to be steeper than normal, so that would indicate a vertical stretch. Okay, so did that happen? Did I see my graph flip? Yeah, I absolutely did. Does it look like the slope of the blue line is steeper than the slope of the red line? Yeah, it does. Okay, so the flip is because of the vertical reflection. Another way to write vertical reflection is a reflection in the x-axis. Okay, and then we notice that the slope got steeper. So that's because of the vertical stretch by 2. Okay, let's go ahead and do this example number 5. Again, I'm going to skip the XY chart for now. That's just to check our work. And I'm going to skip x-intercept. Here the slope is -1/4 and the y-intercept is 0, 1. Really, I should already be noticing that there's 1, 2, 3 transformations that should happen. The negative is our reflection. The 1/4, ooh, would that be a vertical stretch or shrink? It's going to be a shrink because it's less than 1, bigger than 0. And then +1 is going to be up because it's +1. If it was -1, it would be down. Okay, so let's go ahead and graph both our parent function and this works to do corner to corner because it's a 10 by 10 square graph. If it wasn't a square graph, or if it wasn't 10 by 10, you might want to be more careful about graphing the parent function this quickly. Okay. To graph the blue function, I graph 0, 1, and then I'm going to go down 1, right 4, down 1, right 4, okay, and draw a line through those points. Okay, what happened? It flipped. It looks like it flattened out. And it looks like this origin point moved up 1. Okay, so 3 things. It flipped. So that's going to be your vertical reflection. You can also write reflection in the x-axis. It flattened, or less steep. Which would be a vertical, oops, let me go ahead and write this, vertical shrink. And we'll put by, we actually know exactly what it's by 1/4 because of the equation. And then we can see that it shifted translation Actually, I'll even write vertical translation, just so we're specific. Down 1. Okay. Oh, it wasn't down 1, it was up 1. Keeping you on your toes. All right, up 1. And again, that's because we had the +1 in the formula. All right, so for linear equations, we talked about different transformations, right? If there was a negative out front, then that's a vertical reflection. If A was bigger than 1, that was a vertical stretch. Where if A was between 0 and 1, then that was a vertical shrink. And then what did B tell you? That was your up-down, right? That's your translation. Works the exact same with absolute value. So like, what do you think is going to happen if you have a negative out front? Again, it's going to be a vertical reflection. A value, that's going to be your vertical stretch or shrink. If it's a number other than 1, right? If it's bigger than 1 or if it's less than 1, greater than 0. And then again, B is going to be up, down. The translations work the exact same. What you have to note is what your parent function looks like. So a linear equation has a line for the parent function. An absolute value equation is going to be a V shape. Okay, so you just have to know the parent function, and then you can transform it according to the reflection, stretch strengths, and movements up and down. So here for absolute value, it wants you to graph the absolute value function in red, which we know that that's going to have a V shape. And then we're going to graph 2 times the absolute value of x in blue, which, because 2 is a number bigger than 1, we should be expecting a vertical stretch to happen. Okay, so let's start just by graphing the absolute value of x. This is your parent function. Okay, that's the most basic absolute value function you can have. So let's grab some points here. I'm going to just pick some negative x values, 0, and some positive x values. Okay, when you plug in -2 into the absolute value bars, what happens? Like if I plug in 2 into the if I plug in -2 into the absolute value of x, what happens? It just becomes positive, right? If I plug in -1 into the absolute value of x, what happens? It just becomes +1. If I plug in 0, what happens? 0. If I plug in 1, what happens? 1. Plug in 2, I get 2. Okay, so that should form our V shape. We have the point -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. See how it forms a V? Where on the left-hand side it has a slope of -1, and then on the right-hand side of the origin it has a slope of +1. This is your parent function. This is the most basic type of V-shaped function. Okay, now what we're going to do is we're going to graph 2 times the absolute value of x. Okay, so again, let's choose those same points, -2, -1, 0, 1, 2. What's going to happen? Well, if I plug in -2, the absolute value of -2 is +2, and so I'd end up getting 2 times 2, which is 4. Okay, if I plug in -1, what do I get? That's going to be 2 times 1, which is 2. If I plug in 0, what am I going to get? 2 times the absolute value of 0. That would be 2 times 0, which is 0. Okay, what am I going to get if I plug in 1? 2 times the absolute value of 1 would just be 2. And g of 2, if I plug that in, let me put the absolute value bars. That's really just going to be 2 times 2, right, which is 4. So I should have the point -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. looks like this. All right, and really, you can see that what ends up happening to the V is that it gets more narrow. That's because as you grab these lines and pull them upwards, right? Think of like a rubber band that you're pulling upwards. It's going to actually get more narrow when you're doing a vertical stretch. Okay, so that's why up all the way back here, we say that it either narrows the graph or steepens the slope, because when we see our V shape, a vertical stretch with the V shape, it actually causes the graph to narrow, which is interesting. Okay, so when going from f of x, which is the red graph, to g of x, the graph gets what? We said that the graph gets more narrow. It says, explain how g of x is a vertical transformation of f of x using words from the vocabulary word bank. It would be a vertical stretch by 2 if it's getting more narrow. Okay, that's it.